There we go. All right. See, when you clean your house, you move things and then you can't find your headset for class. All right. Sorry for that delay. Let's get this going. All right. So welcome back. The usual stuff, the usual notes for due dates and test dates and such are, are here. So we said that our chapter 7 and 11 test is going to start this Wednesday, the 29th. And that'll be up by midnight, and it will end Sunday, May 3rd by midnight. The review, I'm going to post no later than tomorrow by 1:30. I'm going to do my best to get it done today. I'll shoot y'all a message when I have it done. Again, I'm going to really try to get this done today, but I will at least have it ready before your testing starts. So remember, this test 3 will be the last one where you have a span of days. I'm also going to make the homework due the same day as the test. Per usual, I would prefer that you have that done the day before the test. I would prefer you have all these things done way before everything's due, just in case there's some weird glitch in the matrix system, whatever, and my math lab is down on a Sunday, which nobody wants that. And then our final is going to be on Wednesday the 6th, so that's a week and a half away. It's going to be a 24-hour period only. You will get a review per usual. It may be a little different. It may be just me telling you specific problems to study previously. I may build another review assignment. I haven't decided yet how I want to play this out because I want to do the final just a little different from the tests. Obviously, giving you only one day, and I'm likely to ask you to submit your work on Canvas for this one. I really think I'm going to, and I'll have to give a time limit where you have like 10 minutes to submit it in Canvas after you have finished the exam. We'll talk more about that later though. So for now, and I know this at the very top says 11.1, but this is 11.2 as well. So we have covered the first 2 sections of chapter 11. 11.1 was on sequences and summation notation. So we learned what a sequence was. It's just a bunch of numbers separated by commas, when you're giving your answer, but there's a pattern with them. There's a formula, whether it's based on the index or it's based on a recursive formula. So that's when the next term is based on the previous term, like this. Then we introduced our series notation along with factorial notation. So some definite new stuff in here, but it's nothing absolutely crazy. It's just more stuff with formulas, really, plugging in numbers, pattern recognition, which we hope that over your past several years of math, that you're starting to get some pattern recognition. But this summation notation, this is, I don't want to say it's a doozy for some people. It's just some people don't want to spend the 10 minutes memorizing that this number is where you're starting your index, this number is where you're ending. And then this right here is just the formula that tells you, hey, plug in this number for I, plug in this number for I, and do this to it, multiply by 3, add 7, square it, whatever. Some people think this Greek letter means something else. It's just telling you to add all of the numbers in sequence at the end. And we found a bunch of sums. And then in the next section, we developed a couple of formulas. We've developed a formula for finding an nth term as long as there's a common difference or constant difference between all the terms. In other words, the next term is the last one, plus or minus the same number over and over and over. We also said that can really very easily describe a recursive situation, which I literally just did. You take the last term and you add the same number over and over and over again to get the next one, the next one, and the next one. And we kind of logicked our way through this formula. And then we said, all right, if you know your sequence is arithmetic, if you know that the first term plus 2 is the second term plus 2 is the third term plus 2 is the fourth term, then there's actually a rather clever formula to find that sum. As long as you have a finite number of terms, it doesn't matter if you have 100 or 1,000 or a million or a billion or a trillion terms. All you do is you take the number of terms and you multiply that by the average of the first and the last. I said this is the green is the official formula. This black version is just a slightly different algebraic version of it, but I like this black version because it gives us just a way of relating it. So again, the number of terms in times the average of the first and last terms. Of course, you could just say this is half of the number of terms times the sum of the first and last. I mean, you can rationalize just about anything. I really want to make a joke about something our president said, but I don't want to have it recorded, so I'm going to pass. But you can probably guess what I want to say about rationalizing just about anything. All right. So then we practice using that formula a couple of times, because if you only had to find the sum of the first 3 or 4 or 5 terms, honestly, there's no reason to use this formula unless the sequence is just crazy. But we're not going to be dealing with crazy sequences in this course. We deal with things like 5i minus 9 and I squared and things like that. Although I squared is not arithmetic, we still deal with it. So usually we're asked for a larger sum, like the first 25 or the first 100 or the first 10,000. And the point of that is we don't want students just going to their calculator, figuring out what the first 10,000 terms are, and then hitting the plus button 9,999 times. That would be silly. So we say, hey, if there's a mathematical formula that can get us the answer a lot quicker, hey, find the first term, find the last term. You gotta know the number of terms, and those 3 things give you the answer, but only if they're arithmetic. So this was arithmetic, and we showed that because we found the first 2, 3, 4 terms. You have to find at least 3. The first 2 will tell you what the common difference is likely, and then as long as that holds up for the next 1 or 2, then you're good. So once you have those numbers, the first term, the last term, and the number of terms, it's just plugging into the formula. So then there was another one. We showed that it was arithmetic. We found the last term. We plugged our 3 numbers in. And we did another one. We had the first term. We knew the common difference, so we know this is arithmetic. So we found the 66th term by using that previous formula. Hey, you can find an nth term by taking the first, adding the d 1 less time than the number of terms you're trying to find. So that gave us our last term. We have our first, our last term, and the number of terms. We applied our formula. So again, arithmetic sequences are sequences that have a constant or common difference. They have the same change each time, whether it's a +5 every time or a -2.5 every time. So that is going to be enough chit chat on 11.2 and 1, just kind of regurgitating everything. Let's move on to 11.3. And let's spell properly. Geometric sequences and series. Actually, before we do that, so 11.2 was arithmetic sequences and series. An arithmetic sequence or series is one in which the next term is the previous term plus or minus the same number every time. Now, it can't be plus one time and minus another. It has to always be plus or always be minus. There's no alternating with an arithmetic series. A geometric sequence or series has a strong relationship to the arithmetic. It's that you can take, say, the 5th term, and to get the 6th term, you do one thing to it, and then to get the 7th term, you do the same thing to the last one. You do the same thing to the last one to get the next one. You do the same thing to the last one to get the next one. But instead of adding, whispering, or subtracting the same number over and over and over and over, we're going to multiply by the same number over and over and over. So a geometric sequence or series is one in which the next term is found by multiplying the previous term by a constant. This constant is called the constant ratio. The constant ratio is literally the ratio between the next term and the previous term. Sorry, getting my pen. That was all purple last. Interesting. All right, so that's saying a to the n. Let's use r actually. R equals a to the n over a to the n minus 1. So we use the letter r for ratio. Does this letter matter? No. It's just a helpful way of remembering it. C for constant, right? No, we did D. D for constant difference or common difference. R for common or constant ratio. And the words common and constant, they're completely interchangeable. So, given, let's say we were given silly pen, given a first term and the constant ratio. Did not mean to write an equals. I meant to write a colon. That says that the second term, a sub 2, would be the first term times r. Now, of course, I didn't really need to write that dot, and that's going to be the last time I write it. So the second term is just the first term times r. Okay, the third term would be the second term times r. But the second term we just said is this a1 plus r. I said plus, I meant to say times. The second term we just said is the first term times r, so we can replace that. So this would be equal to, and I'm going to use red to show the substitution, a1r times r. But guess what? R times r is r squared. That's a1 times r squared. The fourth term would be the third term times r. Again, if your sequence or series is geometric, it means that the next term is the previous term times r. But we just said, we just said that the third term, actually let me use a different color. We just said that the third term is a1 times r squared because it was the second term times r, which was the first term times r times r. I hope that you can see where I'm trying to go with this. So this would be, again, instead of writing a3, we'll write a1 times r squared. But that extra r at the end stays. And that's a1 times r to the third. So pattern recognition. Let's see if we can get it. The second term we broke down as the first term times r. The third term we broke down as the first term times r squared. The fourth term we broke down as the first term times r cubed. So I'm willing to bet that the fifth term is the first term times r to the, what do you think? Fourth. Then the fifth term would be the first term times r to the, I think I just said that. The sixth term would be the fifth term times, Lord. The sixth term would be the first term times r to the fifth. The 10th term would be the first term times r to the 9th. The 20th term would be the first term times r to the 19th. So we can get this pattern that the nth term is just the first term times r to the n minus 1. This is what we're trying to develop with that pattern. And this is in general. So if we know that a sequence or series is geometric, all we need is the first term and the last term to find any particular term. The cool thing is, when we want to find a sum for this type of sequence or series, all we really need is the first term and the constant ratio, because the last term is based on those two things, and the formula, similarly to the arithmetic one, is going to break down to something as a formula involving first, last, and that constant number. So let's try this out. Example 1. And we are going to find the seventh term in the geometric sequence with, and I'm only going to do one of these, the first term being 2, and the constant ratio between them being 3. So I could find the second term, I could find the third term, I can find the fourth term. To find the second term, it's the first term times 3. To find the 9th term, it's the 8th term times 3. To find the 2 millionth term, it's the 1,999,999th term times 3. That's what this R says. So the second term would be 2 times 3, which is 6. The third term would be 6 times 3, which is 18. The fourth term would be 18 times 3, which is 54, etc., etc., etc. But we only want the 7th term, and we don't need to find the 2nd through 6th term to do this. We can just go straight to saying, okay, a sub 7 would be the first term, a sub 1, times r to the n minus 1, and 7 minus 1 is 6. This is the formula to find the 7th term. But our first term is 2, so that's 2 times. Our r is 3, so that's 3 to the 6th. Right, so 3 to the 6th, that's the same thing as 9 cubed, which is 729. So this is 2 times 729. And then that would be, was that 1458? Yes, 1458. So that's the 7th term of the sequence. It's not a very complex formula to use, so that's why I'm not going to do a whole bunch of examples with it. The only thing is, when your R is a positive number, and it doesn't even have to be a very big number, that R was only a 3. 3 is not a large number. By the time you get to the 7th term, we're at 1458. The next term would be 3 times that. I'm not doing that in my head. That's 4,374. I pulled out my calculator. So the 8th term is 4,000 something. Then the 9th term would be 13,000 something. Then the next term would be the 39,000 something. That's the 10th term. So we're at the 10th term and we're already at about 40,000. The next one's going to be about 120,000. These things grow very, very fast. Basically, every 2 terms, we're going to grow in what we call an order of magnitude. If you've never heard of that, an order of magnitude just means a factor of 10. So every 2 terms, we are now about 10 times larger than 2 terms ago. That is very, very fast. This is basically exponential growth, and you can probably tell that because the formula that gives us the sequence is exponential, right? We just kind of keep plugging a number in here because we keep multiplying by another r. Now you might say r to the n minus 1 is an exponential, and you're correct, it's not. But this is the same thing as constant percent growth, which leads to exponential functions. Because it's recursive, you end up multiplying by 3 over and over and over and over, which is the idea of exponential. Because our exponent is our exponent's the variable, not the base. All right, so again, it's really, really cool and clever to see the derivation of some of these formulas. And unfortunately, the amount of time it takes is not so fun. I'm thinking about this. I'm going to show you the formula, and let me think if I have enough time or not. Okay. To find, please let me type. To find the sum of a geometric sequence or series, I mean, it's going to be a series. Let me just say series. All series have a sequence in them. So to find the sum of a geometric series, you use the formula we're going to go S sub n. So this says the sum of the first n terms is equal to the first term times 1 minus r to the n divided by 1 minus r. Sorry about that. My dog came and panicked and he needed to go out really bad. Okay, where was I? So to find the sum of a geometric series, use the formula. The nth sum, so that's the sum of the first n terms, is a sub 1 times 1 minus r to the n over 1 minus r. And I want to fix this little r here. There we go. Make that a little prettier. So that's our formula. And I am actually going to do the derivation. I think we have enough time because I don't know that I want to get too far into the next chapter today. So we're going to do a proof. We haven't done any proofs in a while. Let's just show what S sub n represents. It's the sum of the first term plus the second term plus the third term plus blah, 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 blah. Then it would be the a sub n minus 1 term plus a sub n. So that's just saying the first to the last terms. That's what we're adding. Okay, now this proof, what I'm about to do, comes completely out of left field. But here's the thing about math and finding new maths along the way, just to say that as terribly as possible. Sometimes you have to do things out of left field. Sometimes you have to think outside the box. And it's one of those things that education is not necessarily that great at. We tend to tell you to think inside the box by teaching you methods and manners and how to do this in a certain sequence, pun intended. But really to get new creative ideas and formulas and things, somebody at some point has to do something different. So, don't stagnate, try things out, randomly do things and see what happens. And, 99.9% of the time, nothing comes out of it. But 1 out of 1,000, 1 out of 1,000,000 times, you change the rules, you change the game, and you come up with something like this. So some mathematician decided that we are going to do this thing. What color do I want next? We'll go with green. So let's multiply both sides of this by r after changing each term. By changing each term, I mean, let's write that each term is the first term times an r. So that's what we're going to do after this. Was it this? So S sub n, that's a sub 1 plus. So I'm not multiplying anything yet. A sub 2 is just a sub 1 times r, plus a sub 3 would be a sub 1 times r squared. Each term, each nth term, is the first term times r to a power 1 less than the term it is. So the first term is the first term, the second term is the first term times r, the third term is the first term times r squared, the fourth term would be the first term times r cubed. And you keep going until you get to the last couple. So the n minus 1 term would be the first term times r to the n minus 2, that's 1 less than the exponent, plus then a sub n would be the first term times r to the n minus 1. So that's the after part. After changing each term to just a product of the first term and the constant ratio, because every term can be written that way if it's geometric. So we're assuming it's geometric. So now we're going to do this. Now we're going to multiply this thing, both sides, by r. So let's go with orange. So we take r times s sub n. So I'm just taking the previous line, and I'm going to multiply every single thing by r. So that's a sub 1 times r plus a sub 1. Now, this was a sub 1r previously. If I multiply it by another r, it's r squared. See, every term is going to get an extra r. So that's why this is r times s sub n. That's why this is now a sub 1 times r. A sub 1 times r squared. The next one would be a sub 1 times r cubed. The next one would be the first term times r the fourth, etc., etc., etc. Now this r to the n minus 2, if you multiply that by r, you're going to get the first term times r to the n minus 1. All you're doing is adding 1 to each exponent, and negative 2 plus 1 is negative 1. And plus, this last term is the first term times r to the n. R to the n minus 1. If you add 1 to n minus 1, you get n. So again, I'll make that little memo that each exponent added 1 on the right-hand side. That is what has happened. So now what we're going to do is, I really wish I had just a little more room. We're going to take these two rows. So this purple is a row, this orange is a row. We're going to call this a system of equations. So if you remember what a system of equations, it's just multiple equations written at once in the same parameters. And this is not something we would normally want to deal with in a sequencer series, but we can treat any pair of equations as a system. So we're going to treat this like a system, and well, you learned back in pre-calc 1 that you can add and subtract two equations to each other and do whatever you like, really. So let's take these and let's subtract them. So we're going to subtract this system. So the left side, we're going to have the purple minus the orange. So it goes s sub n minus r times s sub n. Now remember, each s sub n represents a sum of terms. But we don't have to worry about that too much. Let's just think about it as an algebraic quantity, s or x or whatever, because that's going to be important. Now on the right-hand side, you're going to have all these purple terms minus all these orange terms, and that's going to get really, really tedious. Let's just see if we can verbally go through this without having to write all of that. So we're going to have this purple a sub 1. It's not red because I'm changing colors. So that's this term. I'll circle them as I use them. How about that? So we use that term. Then the next term is this a sub 1 r. So now we have this term. And then it would be the next one, the next one, the next one. But I don't want to do that. I want to now start subtracting off the pairs of the orange. So we're subtracting. So it's always the top thing minus the bottom thing. The a sub 1, there's not a bottom thing that's similar to it. That's why I went ahead and wrote it. This a sub 1r, we're going to subtract this a sub 1r. Well, they're the same thing, so they cancel. So we've used that one. Now let's do the next purple one. So a sub 1r squared. So that was this one. Now let's subtract the next orange one. So minus a sub 1r squared. They cancel. Plus data, 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 data. We have this one, a sub 1 r to the n minus 2. Now I didn't write it, but it is in here. It's about right here. So that's a minus a sub 1 r to the n minus 2. So those cancel. Then plus the a sub 1 r to the n minus 1 from the top, the first term times r to the n minus 1, minus the orange one on the bottom. So they cancel. Now there's no more terms at the top, so I don't add anything, but there's still one more term to subtract from the bottom, and that's the minus a sub 1 r to the n. The point of this whole thing is that we just had potentially infinitely many terms being added and or subtracted, combined, but almost every single pair of them cancels because with that extra r, you get a matching term just shifted one index off. But not everything cancels. So what are we left with? On the left side, we have s sub n minus r times s sub n equals, that's the first term a sub 1 minus the first term times r to the n. Well, what we can do here is we can factor. And on both sides, there are GCFs on the left side of s sub n on the left and a sub 1 on the right. We're almost home free. So we go s sub n, parentheses. When you take it away from the first term, you're left with 1, minus. When you take it away from the second term, excuse me, you're left with r. When you take a sub 1 from these, it's very similar. When you take it away from the first one, you're left with 1, minus. When you take it away from the second, you're left with r to the n. And then what we can do is, we can solve for s sub n. We can divide both sides by the 1 minus r. To give us the formula we saw previously, s sub n equals the first term times 1 minus r to the nth over 1 minus r. There's our proof. It only took about 10 minutes. That's fine. I think this is a pretty important proof because it really does just kind of pull out of thin air a technique. How did some mathematician figure this out? Because he tried doing 10 million different things and stumbled on this, most likely. To a sub 1 r cubed in orange. So someone just asked, what happens to a sub 1 r cubed in orange? So every next term is going to subtract off a previous term. So I'll show in red. Right here in the top would be the positive a sub 1 r cubed, and that will subtract this a1 r cubed, and they will cancel each other out. Sorry I didn't explain that one, but yes, every single one in the middle cancels. So 1, 2, 3, the fourth term from the top will cancel the third term from the bottom. The fifth term from the top would cancel the fourth term from the bottom. The 17th term on the top would cancel the 16th term on the bottom. The only things that don't cancel are the first term from the top and the last term from the bottom. Sorry about that. I did not mean to leave you hanging on that one particular term. Thank you for asking. So again, very, very cool formula. And this one is even cooler than the arithmetic sequence. And we'll see why that is in a bit. But let's practice the formula for now, at least. Where did my page go? Problems. Here we go. So example 2. Oh, I'm gonna have to insert a page. That's not how I wanted that to happen. Maybe if I just kind of click down here. Nope. All right. Why? It was working before where it would do it after. Now it only wants to do it here. All right. Well, the proof's just below. No worries. I'm not going to sit here for 5 minutes worrying about that. Example 2. Find the indicated sum. This will be example A. Oh no, I think I'm about to crash Word. I've done too much. All right, well, let's see how long this will work. The sum of I equals 1 to 4, to 5 to 5. There's a 4 in the problem. of 4 to the I. So we're going to find the indicated sum. I know that's very specific sounding. It just means find the sum of the series, the sum of the sequence of the first 5 terms of 4 to the I. Now, I did not tell you this was arithmetic. I did not tell you this was geometric. So that means you have to show that it's one or the other. So if you have to find a sum of a bunch of terms, now clearly this is only 5 terms. Yeah, you could just do 4 to the first, 4 to the second, 4 to the third, 4 to the fourth, 4 to the fifth, and then add them up. That would not be the end of the world. I think that's obvious. But if I ask for the first 8 or 12 or 50, that's going to be a little more of a pain in the butt to have to find all the individual terms. So it's much more in your benefit to show that a sequence is arithmetic or geometric, if you're lucky that they are. So let's say a sub 1 would be 4 to the I, 4 to the first, which is just 4. So the first term is 4. The second term would be 4 to the second. It's just 4 raised to the power of the index. 4 to the second is 16. Now, if this sequence was arithmetic, you'd say, all right, the difference of these is 12, and then the next one would be 16 plus 12, which is 28. But 4 cubed is 64, not 28, so it's not arithmetic. We're not just adding the same number over and over to get to the next term. And I think that with practice, that becomes obvious because you're involving an exponent. Exponents don't mean you're just going to add to get to the next one. So instead, let's try the ratio, and I really wish I could change colors, but I think you can tell that that is now broken in Word. Gotta love technology. So a sub 3, I'm sorry, not a sub 3. Let's see, a sub 2 divided by a sub 1. Remember we said that that constant ratio is the ratio between the next term and the previous term. That's why I'm doing a sub 2 over a sub 1. That's 16 over 4, which is 4. So if the third term is the second term times 4, oh no. Did that do it? Yep, that did it. All right, let's see what happens. That's not us. Don't worry about all that stuff right there. This happened in another time. I don't know if it was our class or someone else's, another class I was teaching, but I guess if you start drawing too much, it overloads everything. That's the proof. Here we go. All right. At least it didn't delete everything. So once again, we took the ratio of the second and the first term, the next and the previous, and we came up with 4. Now, if the next term, if a sub 3 is just a sub 2 times 4, then we're good. So a sub 3, oh, there we go, black works now. Using the actual formula, that's 4 to the third, which is 64. So let's try this using the R. Let's say is a sub 3 equal to the first term times R squared, or the second term times R. Well, the second term times R, the second term is 16. The R we came up with is 4, and it's 64. So yes, it works. So now we know R is 4 definitively. If you don't trust this, go to the fourth term. 4 to the fourth is 256, which is 64 times 4. So therefore, we can say that we can use this formula, the sum of the first 5 terms for a geometric series. And that's that blue formula written above. It should be the first term, and I'll do this in blue to show that I'm using the formula. It's the first term times 1 minus the R, which is 4, to the amount of terms we want, which is 5, over 1 minus the R, which is 1 minus 4. But a sub 1, the first term, was 4, so that's 4 times 1 minus 4 to the fifth over 1 minus 4. Don't let the fact that the first term and the R are the same confuse you, please. The first term could have been 3 or 12 or 17. It doesn't matter. It just happened to be that the first term was the same number as the r. Again, please don't let that confuse you. This number right here does not have to match the other 4s. All right, so 4 to the 5th, 64, 256, 1024. So we have the 4 in front times 1 minus 1024. Over 1 minus 4 in the bottom is negative 3. 1 minus 1024, that's 4, times negative 1023, divided by negative 3. I'm not going to do that in my head. It's not the end of the world. 1023 times 4 divided by 3 is 1364. And the negatives cancel each other out to get you 1364. That is the sum of the first 5 terms. That's just the first 5. The 6th term is going to be vastly larger than the 5th term, which when you add that to the sum of the first 5 would make that sum vastly larger. Geometric sequences and series have the ability to grow really, really, really quickly. It does not take a very large base for your exponential term, which is generally how geometric series are written out, as an exponential of some sorts, generally. I'm not going to say all of them. So if this 4 was a 7, oh man, this thing is going to be really big. If this 7 was a 10 million, I mean, it's going to become an unfathomable number really quickly. All right, let's insert another page. Let's see if this is going to fail again. Nope, we're good. Perfect. B. The sum of, from I equals 1 to 8, 6 times 3 to the power of I. Now again, I know that some student is probably going to just find out what all 8 terms of this are and then add them up. And that doesn't make me happy, but it works. But it's not going to be very friendly if this was an 80 or an 800 or an 8,000, or even if it was just a 15 or 16. It is in your, what's the word I want to say? In your benefit to understand these formulas. You're supposed to be memorizing these formulas, in fact. So I don't know just off the cuff that this is geometric without having done, say, 10 or 20 or 50 of these. Now, I may actually know that it's geometric based on the format, but I'm saying we in general don't know that because we all have different knowledge. So we need to show that this is geometric if it is. Maybe it's arithmetic. Now, I know it's not arithmetic because I see the index as an exponent. That's a really good hint that it's not arithmetic. So let's find the first term, a sub 1. That would be 6 times 3 to the first. 3 to the first is 3. 3 times 6 is 18. A sub 2. That would be 6 times 3 squared. 3 squared is 9. 6 times 9 is 54. Let's do the ratio of these. So if this is geometric, R is equal to a sub 2 divided by a sub 1, which is 54 divided by 18, which is 3. Maybe you start recognizing patterns really quickly and you go, wait, this is a 3. Look at the base of the exponential. That was a 3. Look at the previous problem. The base was a 4 and the R ended up being 4. So if the base was a 5, I'm willing to bet that the R is 5. If the base is a 12, I'm willing to bet that the R is 12. But we still need to prove that this works. So in another color, we'll do red. Let's find a sub 3, which is 6 times 3 to the third, which is 6 times 27. That's 162. So is a sub 3 equal to a sub 2 times R? Well, that would be 54 times 3, which is 162. So it is geometric. So we can say that each term is the previous term times R, which in this case is 3. So if I wanted the 99th term, take the 98th term times 3. Or I can just say that the 98th term is the first term times r raised to the 97th. You don't need to actually find all those terms because we had this formula to find any term previously, just like we had a formula for an arithmetic sequence to find any term based on just adding that d a certain number of times. So that tells us that the sum of I equals 1 to 8 of 6 times 3 to the I is equal to S sub 8, the sum of the first 8 terms of a geometric series. Now, yes, we use the same letter, whether it's arithmetic or geometric, so you just have to know which one you're applying it to. You have to have said somewhere or know that, oh, it's geometric, use the geometric formula. Oh, it's arithmetic, use the arithmetic formula. And they are very different formulas. So this was the first term times 1 minus the r to the nth term, which we want 8 terms total, over 1 minus r. Well, the first term we said was 18. 1 minus the r we said was 3, so that's 3 to the 8th, over 1 minus 3. And 3 to the 8th is a big number. It's 6,551. So this would be 18 times 1 minus 6,561. I think I said 51. 1 minus 6561 over 1 minus 3 is negative 2, which is 18 times negative 6560 all over negative 2, which the negatives cancel. That's just 9 times 6560, which is 59,040. So the sum of the first 8 terms of this sequence is 59,000 and change. So that's how we can use the geometric formula. You have to know that the sequence or series is geometric to use it. If you want to use the arithmetic, you have to know that the sequence or series is arithmetic. Now, if you've done 30 or 40 of these, maybe you don't actually show your work for proving that you have an R or a D, whichever it is. That's okay as long as you've done enough of these to be absolutely certain. But I'll tell you, every once in a blue moon with some of the funkier versions, it looks like they're arithmetic and they're not. Or it looks like they're geometric and they're not. There can be subtle changes to these that make them not what you think. So I really do advise you, find your first and second term, show the third term fits the pattern, heck, show the fourth term fits the pattern if you don't feel confident yet, and then go and apply the formulas. That's the key to success. All right. That's really weird. I can click there, but not here. I guess I have to do that for each page. All right, I'll just write this out. So let's try to find an infinite sum for the first time. And we're going to do this for a geometric only. And we're going to require one specific thing. We're going to require that the absolute value of R is less than 1. Now your R can be negative. There's nothing wrong with an R being negative. That would give you an alternating series. So if your first term is 3 and your R is 2, the next one would be negative 6, then positive 18, then negative 54. I think I just did an R of 3. Let me start over. If your first term is 3 and your R is negative 2, you go 3, then negative 6, then positive 12, then negative 24, then positive 48. You're still doubling each time, but you're going to throw in that alternating sign in as well. So the reason we need this R value to be less than 1, any number bigger than 1 is going to cause those numbers to go up. Like I said, even if you start with the first term being 1, and let's say the R is 2 or negative 2. The R is 2, the next one is 2, then 4, then 8, then 16, then 32, then 64, then 128, then 256, then 512, then 1024. And it just keeps getting bigger and bigger and bigger and bigger and bigger, and the infinite sum is going to be infinity. If you add infinitely many terms that are just getting bigger and bigger, the sum is going to go to infinity. It's going to do what we call in calculus diverge. But if you make that R be less than 1, so something like a half, if your first term is 1, the second one's a half, the next one would be a quarter, the next one would be an 8th, then a 16th, then a 32nd, then a 64th. That's going to make each term go to 0. So what this does is it makes or forces each nth term go to 0 as the n goes to infinity. Some arrow notation you should have learned in pre-calc 1. So it makes each term eventually go to 0. It never actually is 0, except at the infinite term, which doesn't technically exist. But say the millionth term is like 0.0000000000000000001. It's practically 0. So by adding these really, really, really teeny numbers over and over, it's not really going to budge the sum, and it makes it so we can get a finite sum. So by requiring that R is less than 1, what this makes happen, R to the n is going to go to 0. This makes the nth term some R to the n. Now, yes, the times a sub 1 is still there, but we don't need to worry about that. We're just worried about this R to the n because that's what's in the formula. So R to the n goes to 0 as n goes to infinity. It makes that term just disappear. And this is something that's very important in the study of calculus, trying to get some terms to disappear at infinity. So let's go back to that formula we had before. It's the same formula starting off. It's this, an nth sum is the first term times 1 minus r to the n over 1 minus r. So now, s sub n, again, was originally the first term times 1 minus r to the n over 1 minus r. But let's take n to infinity. So we get s sub infinity equals a sub 1 times 1 minus, but we just said r to the n, when we go to the infinite term, this is going to become 0. This is such a small number when it's finite, so the millionth or the billionth or the trillionth term, that when you go to forever and ever, it becomes 0 over 1 minus r. 1 minus 0 is just 1, so this is a sub 1 over 1 minus r. So we get that the infinite sum of a geometric series is a sub 1 over 1 minus r. The irony is the formula is simpler. The infinite sum of a geometric sequence or series where your multiplier, your constant ratio is less than 1 in absolute is this formula. It's the first term divided by 1 minus r. That's it. It is very similar to the finite sum, but it is simpler. Right here is your finite sum formula. But when you go to infinity, as long as the r in absolute is less than 1, this term right here goes away because it goes to 0. So you're only left with the other bits. The a sub 1, it's a sub 1 times 1 is a sub 1. The bottom doesn't change at all. This formula is used constantly throughout calculus, throughout differential equations, and engineering. This is a very popular formula that you do not get to forget. Someone just raised their hand. You can ask a question in the chat if you have a question, unless you accidentally hit that. There we go. Didn't you say that r can be negative? Yes, that's why I have this in absolute. So if your r is negative, let's say that the r is negative a half and the first term is 1. So if the first term is 1, the second term would be negative a half. The third term would be positive 1/4. The next term would be negative 1/8. The next one would be positive 1/16. Then negative 1/32, then positive 1/64. That thing, that r to the n, will still go to 0. It just alternates signs along the way. It doesn't actually have an effect at the infinite term. So yes, that's why we have specifically that r in absolute has to be less than 1. So that r can still be negative, but it's only from -1 to +1. So another way of writing this is -1 has to be, oops, not equals. That was weird. Why is it taking me up there? -1 is less than r is less than 1. These are the same two statements. All right, let's insert another page. And let's go to example 3. We should have enough time to finish this. Find the sum of the sequence for A. 1 plus a third plus a ninth plus 1/27th plus da 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 da. Notice the da 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 da, there's nothing after that. This is me saying there is no nth term. This says go forever. That's what the da 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 da, without having like a nth term at the end of it, says. I'm asking you for an infinite sum here. I want you to add up infinitely many terms, and this is not something you're going to do by hand or with a calculator without the appropriate formula. So what we need to do is show that this is geometric, first of all. We need to, second of all, make sure that the r is less than 1 in absolute, and then apply the formula if it is. So our first term is 1. Our second term is a third, which means that if this is geo, the r would be the second term divided by the first term, which is a third divided by 1, which is a third. A sub 3 was the 1/9. And notice that if we take a sub 2 times r, the previous term times the r, which is a third times a third, they just happen to be the same number, you get a 1/9. It works, so it is geometric. So r is equal to a third, and the first term, a sub 1, was 1. So this r being a third says that these terms are shrinking as we're moving. If the absolute value of r is less than 1, if it's between -1 and +1, that causes these terms to shrink as you move forward, because each term is a fraction of the previous one. If your r is bigger than 1, it causes them to grow, bigger than 1 in absolute, that is to say. So this is geometric. Our r fits the pattern, so we can use the fact that the infinite sum should be the first term divided by 1 minus r. The first term being 1. Oops, why did I write a again? The first term being 1, that was given to us. Then over 1 minus r, we said the r is a third. Oh no, a compound fraction. Whatever do we do? Oh wait, we did a whole bunch of compound fractions when we were still meeting in person. Back in those lovely days. Sigh. So there's a couple different ways you can do this. My favorite way is to clear the individual fractions. So let's multiply them all by the LCD, which is 3. The only denominator you see is a 3. So I'll take 3 times the 1, 3 times the 1, and 3 times the 1/3. The reason we do that is to get rid of the compound fraction, so that these 3's cancel. So that's just 3 over 3 minus 1. 3 times 1, 3 times 1, minus 1. 3 minus 1 is 2, so that's 3/2. Also known as 1.5. Nobody cares, fraction or decimal. My math lab might care. Make sure you give it the one it wants. Pay attention to the instructions. If this was like a test question, if it gave you the answer wrong because you put a decimal instead of a fraction, you shoot me an email, you let me know, and I'll give you full credit for that, obviously. That's not the point of the problem. The point of the problem is everything else. I love this. You know what I love about this? We're saying that we can add infinitely many numbers up, and it's just 1.5. The first number was 1. So we are already 2/3 of the way to the total of an infinite sum of numbers by the first term. The second term's a third, which is 1.33. We're only, 3. So we're only approximately 0.17 from the sum of the infinitely many terms. Then if you add that 1/9, which is another 0.111, man, we are ridiculously close. We're like basically 0.1 off from the infinite sum. So what the beauty of an infinite sum is, if they converge like this, especially if they converge rapidly, and this is a big issue in higher mathematics, we don't need all infinitely many of those terms necessarily. If we're just trying to get, say, an approximation to something, if we need like 2 or 3 or 4 decimals of accuracy for something that's adding up infinitely, maybe we only need the first 3 or 4 or 5 terms of that, which Calculus 2 studies vastly. We take regular old functions like trig functions, we turn them into an infinite sum of polynomial terms, and then we can use computers to approximate them with honestly only the first 2, 3, maybe even 4 terms, as long as we don't need super, super accurate decimal precision. So when you talk about numerical methods of mathematics and the study of error ratios and things like that, we really, really, really become reliant on ideas like this. All right, one more and we'll call it a day. So let's have 2 minus 1 plus a half minus a quarter. I'll show a bunch of these terms. Plus an eighth plus da 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 da. So again, the infinite sum. Now notice these are alternating. So R will be negative. We don't have to know that up front. I'm just pointing it out. This is an alternating sequence or alternating series because it goes positive, negative, positive, negative. All that does is it makes the R negative if it's geometric, But we still need to prove that it's geometric. So let's say a sub 1, well, that's 2, that's given to us. A sub 2 is negative 1. And if it's geometric, the R would be a sub 2 divided by a sub 1, which is negative 1 divided by 2, which is, I'm going to write it one more time, it's negative a half. But we need to show that a sub 3, which is negative a fourth, no, excuse me, positive 1/2, positive 1/2. We need to show that it's also the previous term times R. Well, the previous term, the second term, was 1. The R was negative a half. I'm sorry, the previous term was negative 1. I am all over the place with my signs. The second term was negative 1. There's my negative 1. The R was negative a half. There's my R. Negative times a negative is a positive. That's a half. So it is geometric with an R of negative 1/2. Look at that. The R is negative just like predicted. But in absolute, it's still less than 1, so we're fine. If this was a negative 2 or a negative 7 or a negative 50, that would not be fine. We would not be able to find an infinite sum because it would do what's called diverge. It would go to infinity or negative infinity. As long as the R is between negative 1 and positive 1, it converges, which means it has a finite value. So here's our R. We know the first term was 2. So the infinite sum, or that's the first term over 1 minus r. That's 2 over 1 minus, and the r is negative, so we do that double negative jazz. 2 over 1 minus a half. Let's just fix that up as 2 over 1 plus a half. Let's say our LCD is 2, so we're going to multiply all by the LCD, which is 2. So that's 2 times the 2 in the top, 2 times the 1 in the bottom, 2 times the half in the bottom. To get rid of the individual fraction. So that's now 4 over 2 plus 1. 2 plus 1 is 3. So that's 4/3. The first term is bigger than the infinite sum. The first term is 2, the infinite sum is 1.3 bar. The second, if you add the first two together, 2 minus 1 is 1. So that's smaller. Then if you add the next one, that's a half. So 1 plus a half is 1.5. The infinite sum is 1.33333. So what happens as you add each next term, you're actually going to be dancing around the sum. You're going to go a little higher, then a little lower, then a little higher, then a little lower. But as you go to the 20th and 30th and 40th, the distance on each side of that is going to basically go to 0. So the infinite sum is 1.33333. What I'm saying is maybe you get to the 100th term and you add those together and you get 1.35. Then when you add the 101st term, maybe you get 1.32, then 1.34, then 1.328, then 1.339, something like that. You're going to bounce around that sum the whole time. And if you don't believe me, try it out. So we're gonna call it a day there. We have like 6 minutes left. I'm not gonna go into the next section of material. That would not be in our interest. So this is where test 3, covering chapter 7 and 11, will end. So as a reminder, we are probably way down here. There we go. Our chapter 7 and 11 test will start on this Wednesday. I plan on having it open by midnight. For some reason, if that's not the case, I'll let you know. But I plan on having that open by 12:01 a.m. Wednesday, the 29th. And then you'll have Wednesday, Thursday, Friday, Saturday, Sunday to finish that. It's going to be like last time. You'll get 2 attempts. So I'm going to take your best attempt. You're going to have 2 hours. You'll have a review. The review will be very similar to the test. The homework I'm making due the same day. I really, really wanted to have it due Saturday, but I think since we're getting so close, I just want to make sure you have enough time to get it done. Our final is going to be Wednesday the 6th. So you're not going to have too many more days to start getting the final ready, which is why I'm saying, maybe try and take this test Thursday or Friday, get it knocked out by then so you can go ahead and start reviewing everything else, because the final will be cumulative. Again, the final exam will be cumulative. It'll cover everything from the first day we met up until whatever we finish in the next chapter, which is technically the previous chapter, conic sections. And the final exam, this is likely to only be 1 attempt, just a note. I don't think I'm allowed to give 2 attempts on a final. I needed to talk to my department head. So most likely that's only going to be 1 attempt for the final. Again, will be cumulative. You'll get some kind of review for it. There is likely to be a pencil paper submission for that on Canvas. You'll get more details as that date gets closer. If you would like us to submit our work in Canvas for the final exam, how would you like us to have our work? Would you like for it to be scanned and sent via PDF? If so, it might take longer than 10 minutes to fully get everything scanned. That's an excellent point that I will consider moving forward. Pictures would absolutely be fine, whatever you have to do to get it in. So maybe that 10-minute thing I'm not going to be able to do, which is actually why I've been doing these take-home tests as I have, because this was an issue I came up with originally, that maybe not everybody can get me work submitted. But the time issue, if you do it 2 days later, can I really trust that? So I have details to iron out with this complicated situation, and I appreciate you, letting me take the time to figure out what works best for us, because I do have your best interests in hearts. So get some homework done, start studying for this stuff. You'll get more details for that, again, as I iron it out. Have a good day. We'll see you on the internet on Wednesday. This video should be up no later than noon today. Take it easy.